The Information Assassin. Skip to chapter 7 if you want your brain completely destroyed, but this first paradox will already make you question if reality even exists. Einstein called it spooky action at a distance, but he never imagined information could simply vanish from the universe forever. What scientists discovered next breaks every law of physics we thought we knew. Here's what should be impossible. According to quantum mechanics, one of the most tested and reliable theories in all of science, information cannot be destroyed, ever. It can be scrambled, hidden, or transformed beyond recognition, but it must always exist somewhere in some form. This isn't just a suggestion. It's a fundamental law that governs every particle, every interaction, every moment in the universe. Break this rule, and quantum mechanics crumbles. Now enter the black hole, that cosmic vacuum cleaner that devours everything unfortunate enough to wander too close. Light, matter, space, time. Nothing escapes its gravitational grip. But according to our best understanding, when something falls past the event horizon, its information doesn't just become inaccessible. It vanishes completely. Stephen Hawking made the situation even worse in 1974 when he discovered that black holes actually evaporate. They emit radiation, slowly shrinking until they disappear entirely. And when they're gone, every scrap of information that ever fell in goes with them. Poof! Erased from existence as if it never happened. The implications are staggering. If black holes can destroy information, then the universe is fundamentally random and unpredictable. The past doesn't determine the future. Cause and effect become meaningless. The clockwork cosmos that Einstein believed in transforms into a cosmic casino where anything can happen for no reason at all. This isn't just some abstract mathematical problem. Information destruction would mean that identical physical situations could lead to completely different outcomes. Physics becomes impossible, science breaks down, the universe stops making sense. Yet black holes exist. We photographed them, we've detected their gravitational waves, and they're out there right now, allegedly committing information murder on a cosmic scale. But wait, the next paradox makes this look simple. Because at the edge of a black hole, you face a choice that will literally kill you either way. The firewall that shouldn't exist. Remember that detail about information, it becomes crucial for what happens next. At the edge of a black hole, you face an impossible choice: burn alive in a wall of fire that physics says can't exist, or fall peacefully through nothing at all. Both options are guaranteed by the laws of physics. Both cannot be true. This is the firewall paradox, and it's tearing theoretical physics apart at the seams. For nearly a century, Einstein's equivalence principle has been gospel. It states that if you're in free fall, you feel weightless. Gravity becomes indistinguishable from acceleration. This means that falling across a black hole's event horizon should feel completely smooth and ordinary. You wouldn't even know you've crossed the point of no return until the tidal forces begin stretching you apart much deeper inside. But quantum mechanics demands something else entirely. When Hawking radiation escapes a black hole, those particles become entangled with the matter that fell in earlier. Quantum entanglement is nature's strangest phenomenon. Particles remain mysteriously connected regardless of distance. For the black hole to preserve this entanglement as it evaporates, something shocking must happen at the event horizon. The math is brutal and unforgiving. If entanglement is preserved, then the event horizon cannot be the smooth, empty space that relativity predicts. Instead, it must be a wall of high-energy particles, a cosmic firewall that would incinerate anything attempting to cross it. You would be vaporized instantly, reduced to subatomic particles before you could even register the pain. Here's the devastating problem. Both scenarios are required by physics. The equivalence principle, tested countless times and never found wanting, guarantees a peaceful crossing. Quantum entanglement, equally fundamental and experimentally verified, demands a deadly firewall. These aren't competing theories that we can simply choose between. They're both cornerstones of modern physics. 4 physicists named Almheri, Marolf, Polchinski, and Sully proved this paradox in 2012, and the physics community is still reeling from the implications. But this contradiction gets worse because black holes aren't even black, and what they actually do will haunt you. Hawking's vanishing act. Pause and guess what happens when a black hole isn't black? The answer will terrify you. Black holes aren't black, they glow, they shrink, and eventually they disappear completely, taking all their secrets with them. Stephen Hawking discovered this cosmic vanishing act in 1974, and it changed everything we thought we knew about the universe's most mysterious objects. Here's how the magic trick works. Empty space isn't actually empty. It seethes with virtual particle pairs that pop into existence and annihilate each other in fractions of a second. These quantum fluctuations happen everywhere, all the time, but they're usually invisible and harmless. Near a black hole's event horizon, however, something extraordinary occurs. When virtual particle pairs appear at the edge of a black hole, the intense gravitational field can tear them apart before they reunite. One particle gets dragged past the point of no return while its partner escapes into space. But here's the trick. The escaping particle becomes real, carrying away a tiny amount of the black hole's energy. This is Hawking radiation, and it glows with a faint heat signature. The smaller the black hole, the hotter it burns. A black hole with the mass of our Sun would have a temperature of just 60 billionths of a degree above absolute zero. But a black hole the size of a proton would blaze at 100 trillion degrees, outshining the surface of the Sunday. These microscopic monsters would evaporate in less time than it takes light to cross them. As black holes radiate away their mass, they shrink and heat up, causing them to radiate even faster in an unstoppable feedback loop. Eventually, they explode in a final burst of gamma rays and disappear forever. When they're gone, every piece of information that ever fell into them vanishes as well. This creates an impossible situation. The matter that formed the black hole had specific properties: spin, charge, quantum states. Hawking radiation appears to be completely random and thermal, carrying no information about what fell in. It's as if the universe is running a cosmic shredder that doesn't just hide information but destroys it entirely. Physics has no mechanism for information destruction. Yet here it is, happening in slow motion across the cosmos. And this cosmic crime sparked the most brutal intellectual war in physics history, but the winner's discovery will shatter your worldview. The war that split physics. What you're about to learn made Stephen Hawking surrender everything he believed about reality. For nearly 3 decades, two physics titans waged an intellectual war over the soul of reality itself, and the battlefield was a black hole. On one side stood Stephen Hawking, the master of cosmic mysteries. On the other, Leonard Susskind, the street-fighting theoretical physicist from the Bronx. The battle began in 1975 when Hawking made his shocking claim. Information that falls into black holes is destroyed forever when they evaporate through his radiation. This wasn't just a minor theoretical dispute. It was a declaration of war against quantum mechanics itself. Hawking was essentially arguing that the universe could forget its own past. Susskind refused to surrender. He insisted that information must be preserved, even if we can't see how. Black holes might scramble information beyond recognition, but they cannot destroy it. The stakes couldn't be higher. If Hawking was right, quantum mechanics was fundamentally flawed. If Susskind was correct, then something was terribly wrong with our understanding of black holes. The war escalated in 1997 when Hawking made a famous bet with Kip Thorne against John Preskill. They wagered an encyclopedia, specifically Total Baseball, the ultimate baseball encyclopedia, on whether information could escape black holes. Hawking was so confident in information destruction that he was willing to stake his reputation on it. The tide turned with the discovery of the holographic principle and advances in string theory. These revealed that information might be encoded on the black hole's surface, preserved in ways that seemed impossible but mathematically sound. The firewall paradox emerged, showing that information preservation came with its own devastating costs. In 2004, Hawking shocked the physics world. At a conference in Dublin, he conceded defeat. Information is preserved, he admitted, but in such a mangled form that it's effectively useless. He bought Preskill the encyclopedia, while Thorne refused to concede. But Hawking's surrender didn't end the war, it just revealed how little we actually understand. If information survives, then reality itself might be far stranger than either side imagined. Wait until you see the next paradox. It proves that physics literally guarantees 2 impossible deaths at once. The spaghetti death paradox. Before you continue, remember this. What you're about to read violates the most basic rule of logic. Something cannot be both true and false. Physics promises you'll be stretched like taffy and torn apart, but also guarantees you'll float peacefully across an invisible boundary. Both can't be true, yet both are demanded by the fundamental laws of the universe. Welcome to the spaghetti death paradox, where reality becomes a contradiction wrapped in an impossibility. The setup seems straightforward enough. As you approach a black hole, gravity becomes increasingly powerful. But here's the cruel twist. Gravity doesn't pull on every part of your body equally. Your feet, being closer to the black hole, experience stronger gravitational force than your head. This difference in gravitational strength is called a tidal force, and near a black hole, it's absolutely merciless. The math is simple and terrifying. As the gravitational gradient increases, your body begins stretching vertically while being compressed horizontally. You become human spaghetti, pulled into a grotesque, noodle-like shape until your molecular bonds snap and you disintegrate into a stream of subatomic particles. For a black hole with the mass of our Sun, this stretching begins when you're still thousands of miles away from the event horizon. Long before you cross the point of no return, tidal forces rip you apart atom by atom. Death is guaranteed, violent, and inevitable. But Einstein's equivalence principle tells a completely different story. This cornerstone of general relativity states that freely falling objects experience no gravitational effects locally. If you're in free fall toward a black hole, you should feel weightless and peaceful. The event horizon itself is just a mathematical boundary. There's nothing physically special about crossing it. You should sail through smoothly, feeling nothing unusual until you're much deeper inside, where tidal forces finally become significant. The problem is devastating. Both descriptions cannot coexist. You cannot simultaneously be torn apart by tidal forces before reaching the event horizon and peacefully cross through it unharmed. Different observers see fundamentally different realities playing out. Someone watching from far away sees you spaghettified and destroyed. You, falling toward the black hole, experience a smooth and uneventful crossing. Physics offers no way to reconcile these contradictory truths. But this impossible contradiction is nothing compared to what reality actually is. And, number 6, will make you question if you even exist. The reality hologram. Stop for a moment and look around you, because everything you're seeing might be the universe's greatest lie. Everything you think you know about reality, every dimension, every particle, every moment might be nothing more than a projection on a cosmic movie screen. The holographic principle suggests that our three-dimensional universe is actually encoded on a two-dimensional surface, like shadows dancing on the wall of Plato's cave. This mind-shattering revelation emerged from the deepest mysteries of black holes. In 1972, Jacob Bekenstein made a disturbing discovery about black hole entropy. Entropy measures the amount of information or disorder in a system, and for every object we'd ever studied, entropy was proportional to volume. More space meant more places to hide information. Black holes shattered this rule completely. Their entropy wasn't proportional to their volume, it was proportional to their surface area. The bigger the black hole's event horizon, the more information it could contain. But here's the kicker. All that information seemed to be stored on the horizon itself, not in the vast three-dimensional interior. This led to a revolutionary idea. If black holes store their information on two-dimensional surfaces, maybe everything does. Perhaps the entire universe is nothing more than information encoded on some distant boundary, projected inward to create the illusion of three-dimensional space. Think about it this way. When you watch a movie, you see depth and dimension on a flat screen. The holographic principle suggests that reality works the same way. Every atom in your body, every thought in your brain, every star in the sky might be nothing more than information patterns on a cosmic screen you can't even see. The implications are staggering. Space itself might be an illusion. The three dimensions we navigate daily could be elaborate projections of data stored on a two-dimensional surface. Distance, volume, and depth, all just artifacts of how information is processed and displayed. Even more disturbing, if reality is holographic, then the amount of information in any region of space is limited by the area of its boundary, not its volume. The universe has a finite capacity for information, and we might already be approaching the limit. But wait, if space is an illusion, what about time? The next paradox will trap you forever. The time prison. Here's the detail I promised would destroy your brain, and this is where reality becomes a horror movie. At the edge of a black hole, time doesn't just slow down, it stops completely, trapping you in an eternal moment that stretches toward infinity. Welcome to the ultimate prison, where the bars are made of time itself and escape is physically impossible. Einstein's general relativity reveals time's darkest secret. It's not constant. Gravity doesn't just bend space, it tortures time, stretching and compressing it like a cosmic accordion. The stronger the gravitational field, the slower time moves. Near a black hole, this effect becomes so extreme that it creates a temporal nightmare. Here's how the prison works. As you fall toward a black hole, time dilation kicks in with ruthless precision. From your perspective, everything feels perfectly normal. Your watch ticks at regular intervals. Your thoughts flow at their usual pace. You experience time exactly as you always have, blissfully unaware of the cosmic horror unfolding around you. But to anyone watching from a safe distance, you're becoming a temporal fossil. As you approach the event horizon, they see you moving slower and slower, your movements becoming sluggish like a movie played in slow motion. Your final moments stretch out across minutes, then hours, then years. At the event horizon itself, outside observers see you freeze completely. You become a motionless statue, suspended forever at the boundary between space and time. Your image redshifts toward infrared, then radio waves, fading from view but never quite disappearing. To the universe, you become stuck in a single moment that lasts forever. Meanwhile, you continue falling normally, experiencing nothing unusual about the passage of time. You cross the event horizon in what feels like seconds, while the outside universe ages around you. Civilizations rise and fall. Stars burn out. Galaxies drift apart. The universe itself grows old and cold while you remain trapped in your personal bubble of normal time. This isn't science fiction, it's the inevitable consequence of Einstein's equations. Time becomes a one-way street where forward leads to eternity and backward leads to oblivion. The prison has no walls and no guards, but once you're inside, even time itself can't set you free. And if that broke your brain, wait until you discover what's hiding in empty space. The numbers will make you lose your mind. The entropy explosion. The numbers you're about to see will make you question mathematics itself. A black hole the size of a proton has more hidden information than every book, computer, and human brain that has ever existed combined. This is the entropy explosion, where the universe's ultimate information storage devices make every hard drive look like a grain of sand. Entropy is the measure of how much information or disorder a system can contain. For every object in your daily experience, this makes perfect intuitive sense. A library holds more information than a single book. A computer's hard drive stores more data than a floppy disk. Bigger means more storage capacity. The universe has always worked this way. Then Jacob Bekenstein and Stephen Hawking dropped a mathematical bomb that shattered this simple relationship forever. They discovered that a black hole's entropy doesn't grow with its volume like everything else, it grows with the area of its event horizon. And the numbers are absolutely mind-bending. The Bekenstein-Hawking formula reveals that entropy equals 1/4 of the horizon area measured in Planck units. A Planck unit is unimaginably tiny, about 10 to the minus 35 meters. This means that even microscopic black holes can store impossible amounts of information. Consider a black hole with the mass of Mount Everest, compressed into a space smaller than a proton. Its event horizon would have an area of roughly 10 to the minus 70 square meters. That translates to about 10 to the 66 bits of information. For comparison, every atom in the observable universe could store only about 10 to the 80 bits total, and that's if every single particle was used as a perfect information storage device. This cosmic storage capacity defies everything we understand about information and space. How can something smaller than an atom contain more information than objects trillions of times larger? Where is all this information actually stored? And why do black holes seem to break every rule about the relationship between size and storage capacity? Even more disturbing, if black holes can pack this much information into such tiny spaces, what does that say about the fundamental structure of space itself? But these impossible numbers are nothing compared to the cosmic highways Einstein accidentally discovered, and they're probably unusable for the most frustrating reason imaginable. The tunnel through space-time. Einstein accidentally designed the universe's ultimate cheat code, but there's a cruel catch that makes it worthless. Einstein's equations predict shortcuts through the fabric of reality itself. Cosmic tunnels that could connect distant galaxies or link black holes to the Big Bang. These are wormholes, and they represent the universe's most tantalizing and most impossible engineering project. The mathematics is surprisingly straightforward. In 1935, Einstein and Nathan Rosen discovered that general relativity allows for bridges connecting distant regions of spacetime. These Einstein-Rosen bridges are perfectly legitimate solutions to the field equations that govern gravity. On paper, you could step into a black hole in our galaxy and emerge from a white hole billions of light years away, having traveled across the cosmos in minutes rather than millennia. The geometry is elegant and bizarre. Picture spacetime as a folded sheet of paper. Normally, traveling between two distant points means following the surface, a journey that could take billions of years at the speed of light. But a wormhole punches through the fold itself, creating a shortcut that bypasses the normal constraints of distance and time. Here's where cosmic engineering meets cosmic impossibility. These bridges are fundamentally unstable. The moment anything tries to pass through them, even a single photon, they collapse catastrophically fast. The entrance and exit pinch off and separate faster than light can travel between them. You'd be trapped in a rapidly shrinking tunnel with walls closing in at nearly the speed of light. To keep a wormhole open, you'd need something called exotic matter. This isn't just rare, it's matter with negative energy density that probably doesn't exist anywhere in the universe. You'd need vast quantities of this impossible substance threaded through the wormhole like cosmic scaffolding, fighting against the natural tendency of spacetime to snap the bridge shut. Even if exotic matter exists, the engineering challenges are staggering. You'd need to manipulate the fundamental geometry of space and time itself, wielding energies comparable to stellar explosions just to maintain a tunnel wide enough for a single atom to traverse. Einstein's equations promise us the universe's ultimate transportation network, but the universe seems determined to keep its shortcuts locked away behind walls of impossibility. And in the final paradox, we discover that even empty space is lying to us. This will destroy everything you think you know about existence. The quantum vacuum paradox. This final revelation will haunt you forever because it proves that reality is built on impossible foundations. Empty space isn't empty. It seethes with virtual particles that pop into existence and vanish in an instant until a black hole tears them apart forever. This is cosmic alchemy at its most impossible, the transformation of nothing into something through the sheer force of gravity. The quantum vacuum is a restless, churning sea of potential. According to Heisenberg's uncertainty principle, energy can briefly borrow from the future to create particle pairs that exist for fleeting moments before annihilating each other and paying back the cosmic debt. These virtual particles are everywhere, constantly appearing and disappearing in a dance of creation and destruction that happens trillions of times per second in every cubic centimeter of space. Near a black hole's event horizon, this delicate balance becomes a weapon of mass creation. When virtual particle pairs appear at the boundary, the black hole's immense gravity can rip them apart before they reunite. One particle gets dragged past the point of no return, while its partner escapes into space as real, genuine Hawking radiation. Here's the paradox that breaks physics. This process seems to violate energy conservation on a cosmic scale. The escaping particle carries positive energy away from the black hole. But where does this energy come from? The answer is disturbing. It comes from the black hole itself, which loses mass and eventually evaporates completely. But this creates an impossible accounting problem. The original virtual particle pair had zero total energy, one particle positive, one negative. When they're separated, the positive particle escapes as radiation, while the negative particle falls into the black hole, making it slightly smaller. Energy appears to be created from absolutely nothing, then used to power the black hole's own destruction. The resolution requires accepting that empty space has negative energy density, that the vacuum itself is a reservoir of borrowed energy, waiting to be tapped by sufficiently extreme gravitational fields. Reality isn't built on solid foundations, but on an ocean of quantum debt. Black holes have systematically dismantled every assumption we've made about information, space, time, and energy. They've shown us that reality operates on principles so alien to our everyday experience that they read like cosmic horror stories. If these paradoxes can break physics this completely, what else is the universe hiding from us? The answer will change how you see reality forever, and you're not ready for what comes next. Because if black holes can violate every law we thought was sacred, then maybe the universe isn't just stranger than we imagine, maybe it's stranger than we can imagine.